So very good afternoon to everyone. So I am Rohit Gehlot and I will be taking the week's 5 problem session. So firstly, in this week, uh, so I will be briefing about what was discussed in this week, and I will be explaining some of the theoretical concepts. Then I will be moving to small MCQs. Then we will wrap up. If you have any doubts regarding some concept and all, you can write in the text box. So firstly, we discussed about the characteristics X-rays, and also in the last section I am talking about. I briefly discussed about the secondary electrons, different signals. Like secondary electrons is generally utilized for the topography analysis. The BSC signals is generally used for the computational dominance, and then we also. Okay, so and for further for the characteristic X-ray, we can have the quantitative and the qualitative analysis of the elements present in the sample, and then I will be telling also like how the energy is calculated for that such, and also each atomic species has like the X-rays of different energy and wavelength. So like for the energy, one second. Yes, Amjad,
Sir, only we two are in this meeting.
sorry.
We how many? We only two in this meeting.
Actually, your voice is not clear. Can you write in the text box if it's possible? Yes, Amjad. Yeah, go ahead. Yeah. Presently, only two are present. Like meanwhile, they will join more. Okay. So, so for the we discussed in the. I was talking about like what we discussed in the uh, last session, and this week also. So talking about the different signals like SC signal, BSC signals, and also the characteristic X-ray signal, uh, and their different applications. And also I discussed about this like the how the characteristics X-rays are generated, and how this the help of the uh, how the knocked in and how an electron is knocked off from the incoming electron and all. And also we discussed about the EDS and WDS, and also we discussed when to use EDS and when to use WDS depending upon their applications. Further, if we go to the much deeper, then we see that the secondary electrons are generally due to the inelastic scattering. These are also have also been discussed by the discussed in this week's lecture. You can also go and have a detailed if you want to have a detailed knowledge. You should watch the lectures. So for the secondary electrons, these are generally of the inelastic scattering, while the BSC are for the elastic scattering. And then these SEs, SE1, then the secondary electrons are also of like SE1, SE2, and SE3. These are also, I have drawn it here in this image. You can see SE1, SE2, and SE3s. So SE1 is generally for the is generally knocked off from the outer shell of electron from the specific atom, and this is the most important signal. And for the Se2, like the primary electron which manages to escape after several elastic after several elastic scattering. And for the SE3, like high energy BSCs with the specimen chamber or electromagnetic lenses, it produces additional electrons. And generally the SE1, which is the most important for the morphological analysis, like it has the energy lesser than 15 electron volt, and generally they escape from the 10 to 15 nanometer of depth. And also if we see about the spectral uh, the resolution of the SEM, like if we talk about and compare these two signals like SE1, SE2 and SE3, sometimes like at lower voltages you are able to see the much better morphological characteristics. However, at higher like voltages SE2 and SE3 hamper these, and so therefore there is a need to like balance or optimize these voltages, and it also depends on the operator. uh, and the higher the and we can say that the higher the operating voltage, the severe will be the beam specimen interaction, and also at higher voltages more Se2 and Se3 will be produced, and due to which uh, which are going to promote the or hamper your topological details. And also like and further, like I'm taking or quoting this line from the this week's lecture, like that the spatial resolution of the SEM due to the SE1 signal is usually increases with your increase in the energy of the primary beam. However, like uh, at the higher energies, your penetration, like the increase in the penetration of your electron beam into the specimen will increase the interaction volume, which may cause some degradation of the images resolution due to the SE2 and SE3. And when you will be watching the lecture, you will be like you can clearly see there was an image like at lower voltages and higher voltage, like 5 kV, 5 electron volt, 5 kV, 5 kilo electron volt and 10 kilo electron volt, and there was clearly visible that SE2 and SE3 are hampering, due to which your specimen was not clearly visible. And here like you can see your interaction volume. Clearly the SE or secondary electron has the highest spatial resolution because it comes from a depth of around 10 to 15 nanometer compared to uh, other signals. Okay, so I you can see in here also the different signals, like when your electron beam coming in contact with your specimen, different uh, different signals like auger electron characteristics, X-rays, secondary electrons, backscattered electron, and cathodoluminescence are generated. These are named as different microscopy also. And then uh, you see that SC, VSC, and X-rays. Okay, if you see, I have added these two in situ studies of in SEM. These are the advanced features now available in the SEM. So here are some, you can see the growth of some particles or like some phases are clearly visible. This is presently in the BSC mode, and then you can okay, then you are able to. And similarly, if you see this video, it's showing the in situ tensile testing. You can see like how the structure and morphology is changing. Presently, this is running in your acid, like SC signal, secondary electron. So these are some advanced imaging which are happening in recently. So you see that how the crack propagates. Okay, so now this was also discussed, but I just added in briefly like how the raster system works in the SCM. So due to this rastering, due to the raster in SCM, your magnification is increased. Like you can control your magnification as the control the raster, or you can control the scan size or the raster to increase your magnification in the specimen. So you see that your specimen is around 10 micrometer of length, and then you are able, this is your viewing screen of around 100 mm to 100 mm. So your magnification is calculated by uh, your L of your screen divided by your L of your sample, which is linear one. So around 100 mm divided by your 10 micrometers, so you are able to see around 10,000 times magnified image. Similarly, you can adjust this and can enhance or reduce the magnification. And by this way, how your rastering work by point, and in a synchronized manner, your screen, there is a synchronization between your screen and your sample. By this way, you can are able to control your magnification and rastering. Okay, and I have also added the SEM layout and functions, which have already been discussed, so I'm not taking much time in this. I also discussed these signals previously also and in the last class also, but I'm just focusing because if you will be focusing, I'm just focusing more on these because it will help in solving this week's or week 5's tutorial questions. So here I have summarize like these three signals majorly, like SC signal, backscatter, and then the characteristics X-ray. So, and your X-rays are also can be classified into EDS and WDS. Okay, and here you can see that your secondary is the most important signal for if you are doing the morphological or if you want to see your topological details of a specimen. uh, then you can clearly see that this SC typically have the energy less than of 50 electron volts. Also for the high energy primary electrons, your elastic interaction with the nucleus, that's how your backscattered electrons are generated. And then similarly for the inelastic interaction with your electron cloud on the loosely bound outer shell electrons, your secondary electrons are generated. Okay. Then one more important feature. So also there was one more feature for the secondary electron and BSC, which was covered in this week. One more concept, only the SC and BSC, only these two signals vary as surface modulation or surface slope, as your surface slope changes, and these are very sensitive to these, to your surface unevenness. Okay, so the higher the so so the contrast due to this your whenever your surface modulation or a change in the slope appears, you see a typical very high contrast, and you're able to distinguish between your particles different composition. And this is also I covered in the, so your secondary electron yield is inversely proportional to your voltage, accelerating voltage. Similarly, your surface topography reduces with the acceleration voltage. Here you can see this plot. These were covered in your lectures. And then if you come to the backscattered electron and your Monte Carlo simulation, like how your electron beam interacts with your specimen, and how till what depth and your in what longitudinal and lateral dimension it spreads. So if you talk about your backscattered electrons, then the primary electrons which have reversed their path and escape from the sample are called the backscattered electrons generally. And then these are the some of the absorbed electrons which have lost all your energy, and they are absorbed within the specimen. So here your electron beam comes, and here you can see some lines are very intense, and while some are very, and as they go deeper, it gets very less intense, and then at last they get absorbed within the specimen. Then also it comes depends on your specimen to specimen, like with higher atomic number and with lower atomic number. It also depends on this. And if you talk about the lower electron volt or lower voltages, then your interaction volume is small. And if you talk about the higher electron volt, then your electron trajectories will go wider and wider inside the material. And further, there is an influence of atomic number also. And if you talk about the difference between your metal and a non-metallic specimen, then there comes a difference in your literal dimension for the interaction. So your literal width is like spreads like compared to the linear width, because of the scattering cross section gets increased. And like as you go with the higher atomic number, it is quite obvious, like okay. And also further, the your tilting angle uh, also affects your interaction volume. So as your tilting angle increases, or for the electron beam, then this will hamper your interaction volume, and which will affect all the signals and scattering. So these are some of the BSc. So you can see, like as you lower your atomic number, so you have like lower yield of your backscattered electrons. So here it is clearly seen. This is for this first one is for your carbon, which has lower atomic number. Another is your silicon, followed by copper, and then your gold. So from left to right, and your atomic number is going to increase. So here you can clearly see that gold has the highest atomic number compared to others. So it has the higher atomic number, therefore the yield of backscattered electrons are higher. You can see, like firstly the electron beam are coming, then they are backscattering again backward. Okay. And you can also see the literal dimension also. Here it is like around 1 micrometer, and for the gold it is around 250 nanometer only. Okay. So further, like if we move to the factors which affect your secondary electron yield, uh, so if you are like you have if you have lower your voltages, then your secondary electron yield increases and your resolution increases. Because of that, here if you can see that here the spot size is lower, or smaller, or a smaller beam diameter. Further, if you increase the your accelerating voltage, then here you have bigger spot size, and due to the bigger spot size, your secondary electron yield and your resolution reduces. So therefore this also depends on from the sample to sample, and also on the operator's constraints, like how he should modulate for a battery imaging. And here you can also see, like uh, here you are getting a darker image, and here you're getting a brighter, and then some secondary electron escape from this, like and this is the Faraday case, which was also discussed in the live demonstration lecture, if you do remember. So if you like what I was discussing previously in this here, like with the carbon and has the lower atomic number compared to others. So you can see that carbon, for the energy required for the carbon to knock off on the K cell electron, is around 284 electron volt, which is comparatively very high. And so, however, for the tungsten, your energy required to knock off an K cell electron is around 69.5 electron volt. Okay, so you can see that your incident beam has enough energy to knock off K cell electrons from both carbon and tungsten electron. And this way you can calculate your uh, energy of the characteristics X3 by subtracting your work function between for the K line and your these L3 lines, for whichever line you want to calculate. If you want to calculate the characteristic line, then you need to subtract from the L3 to your K. Okay, so this will calculate your characteristic X-ray energy. And similarly, you can like another example here is that uh, so for if you talk about the carbon, then your energy to knock off from the K cell is 284, while energy to knock it from the L3 cell is around 7. So here we calculated it around 277. Or if we talk about the your tungsten one, then energy to knock off from the K cell is around 69.5, and however from the L3 cell is around 10. So therefore we calculated the difference, and we can further for like we can discuss that each atomic species will emit characteristics X-ray of different energy and consequently of different wavelength. Therefore, depending upon what we are studying, like if you're talking in terms of energy, then we go for EDS, and if we considering the wavelength, then we go for the WD spectrometry. Okay, so this is the EDS elemental mapping. So by this you can see that this was your specimen which you did your EDS and mapping, and then you can see where your element is aluminum rich, and here it is your titanium rich, while here it is your iron rich. So you can see that your nickel and cobalt are completely spread in your specimen. However, your aluminum and iron, like iron is present at only these locations here, while aluminum is absent from these, right? Similarly, if you see these spaces also, here your iron is present while the aluminum is absent. Similarly, your titanium also, titanium we can say more or less present homogeneously, but not like cobalt and nickel. Sometimes these are very helpful in your analysis, these elemental mappings. And this is another EDS for a point scan. So if you do a point scan, first one was the EDS analysis, mapping analysis for EDS, and this is a point scan. So here it is your specimen, and then we selected some certain rectangular, not rectangular, point analysis here, where you are seeing this blue portion. Here we did the point analysis, and you can see that in your sample around it gives your analysis in both weight percentage and as well as in atomic percentage. You can see that your zinc is around 43.96%, then your titanium is around 2.23, then your oxygen is around 8. So by this they give your some, you can make some formulas with that. So like maybe some zinc oxide or titanium oxide, zinc oxide and titanium oxide are present, and meanwhile if another phase is where if you see here yeah your zinc and titanium oxide are present in your same specimen, because if you see that from the atomic percent your titanium is around 2%. If you do around TiO2, if you do the formula matching and all, and maybe some another intermediate metallic may also be present. So here another application of this characteristic X-ray is shown. Here it is a line scan was carried out from here to here. You can see here that here is your residual aluminum is present, and here is your aluminum coating, and here is your steel. So a line scan was made, and then you get something like this in your output signal. As you can see that as you go from left to right, as your distance is increasing, your firstly your aluminum content was at the peak. However, it reduces, and then you see a surge in the steel specimen and your residual specimen, residual aluminum also. So these are the way you can characterize or see, like in your fracture analysis also, and in your some other applications also. If you can see, like if there's some segregation or precipitation are made, or at some specific location what happened, why your material was filled, is there some eutectic or other phases were present, and similarly like these kind of studies you can do. And then we talk about the detectors. So Evenhart Thornley detector, which is a SASE detector, is very famous, as already discussed in the lectures. And another one is this one is your BSE detector. It just fits near to the your probe, and also you can see that here this is your secondary electron detector. It is inclined at some angle, and the reasoning for that is also been discussed. So I just uh, brought it for your attention. Now if you see that your role of your accelerating voltage on your resolution and signal to noise ratio, so you can see that your as your this is the radius of interaction volume. This is by this formula it is given by. So as your interaction volume increases, so as your radius as your accelerating voltage increases, your radius of interaction volume increases, right? And similarly with the relation with your atomic number also is like this. And if you talk about the increase in the resolution, then your resolution then decreases the size of your interaction volume with upon decreasing of the electron volt. And similarly here also I have summarized this. You can meanwhile you can go when I will be sharing the slide. And then here also like similar kind of like for different carbon, aluminum, gold, and copper interaction. You can see the interaction lateral and longitudinal interaction. You can see now if we see the trade-off between the specimen pixel size and the electron probe diameter. So here, your in the case one, your electron probe is here. We will not be able to resolve A and B because your overlapping of the signals, right? Here you can see that your the probe is bigger than your specimen, so you won't be able to uh, uh, clearly differentiate between A and B. However, here you see that the larger number of signals generated due to fewer electrons incidence on the sample. So here you will be, as your probe size is lesser than your specimen signal, you can uh, still it is not completely fit. And here your specimen pixel size is around uh, equal to the probe size. So here your working resolution of the SEM cannot be higher than the pixel size, you can see. So your probe diameter should be adjusted every time the operator is changing the magnification. So there the expertise of the operator needs to become. So meanwhile, if you have any doubts in what the theoretical portion I have covered, you can discuss rest, like you can also comment here or mail me further. So like these are some of the problems which I will be solving. So first one is that the interaction volume increases when, one second. So first one is that your interaction volume increases, which we just studied about the formula of the interaction volume and all, and it has also been discussed. So as your mm electron beam energy increases, your interaction volume increases. The second one is that suppose we have a material having two phases, this Al2Cu and aluminum copper solid solution. Okay, as shown in the figure, we want to take an image of this material using SEM. We should use which type of signal to get the maximum contrast? We just studied about for the maximum contrast BSC. BSC signals are the most preference, are mostly preferred. So we will go for the backscattered electrons. Third one is someone wants to characterize the aluminum sample using SEM. He increases the voltage of the incident beam. Which of the following statement is correct? First one is that your interaction volume will increase, the secondary electron yield will increase, backscattered electron yield will increase. So firstly, your backscattered electron yield doesn't depend on your voltage. So this statement is wrong. So first one and second one, yes, interaction volume will increase and secondary electron yield will also increase. So statement 1 and 2 are correct. Depth of field of scanning electron microscopy will increase when. So you know that your relation between your depth of field, working depth, aperture size and magnification, right? So depth of field was around 0.2 times of your working depth divided by your A and M. So working distance increases is the correct answer. Next, if you can see, this is a completely just I saw this image is taken from the video which I showed you, the fracture image. So yeah, whenever you study the fracture image, we go for the SC1 because this has the highest around what I said, like so generally we go for the secondary electron because we don't want to see contrast here. We want to see how the material feel and all topographical changes and all. So we will go for the secondary electron. And another one is that we want to characterize uh, the silicon sample with the SEM. He intended to, one second, someone. Okay, so the silicon sample with SEM, he intended to take images of the surface feature at higher magnification. So he goes with the secondary electron imaging. Will the image improve if he takes the image at highest possible voltage? Generally, it is not the case. We just discussed at higher possible voltage, SC2 and SC3 signal will also come, which may hamper your uh, resolution and all. So change the mode from SC to BSC. No, this is generally not done. So he takes the image at minimum possible voltage. There is a limit to maximum voltage for silicon. Yes, this is right. Now if we move to the next one, during the welding of an austenitic steel, sensitization happens. Chromium carbide formed at the grain boundary, which leads to the decrease in the chromium in the matrix. We are characterizing this sample with the help of SEM. How can we confirm that the precipitate we see using the SEM is enriched with chromium? And so anyone who would like to say or comment? We just discussed this. First one is that EDS line scan at the grain boundary will be helpful. Second one is that the crystal spectrometer can detect X-ray from the light element. So EDS line scan will give the yes will tell you that chromium you can do a point analysis also and mapping also. However, the crystal spectrometer is used in your WDS. So only D1 is the correct answer. So while imaging in SEM to get the best resolution and minimum noise, what should be the relation between the electron probe and this? We just discussed. I just discussed about the trade-off. This one, this 19th slide. So these should be around more or less equal. If it lesser, then it is a problem. If it is higher, then also it is a problem. So now, if the coefficient of spherical aberration increases by 1%, what could be the percentage change in the minimum probe? So the formula was also already discussed. I don't want to solve this. So your d minimum is related by k lambda to the power 3 by 4 times cs to the power 1 by 4. You can solve this. So if you have any doubts, we can discuss, or I will wrap the session. Okay, Amjad. If anyone else? But then I think everyone is fine. So let's meet next week. Have a good evening to everyone, and then see you.